In this lecture, we are going to discuss the CE amplifier in some detail. In particular, we are going to talk about the amplifying action of the CE amplifier, and we are going to talk about what happens when, on top of whatever biasing voltages or currents that are already there in a CE amplifier circuit, you superpose a signal, a small AC signal. So the formal subject of today's discussion is AC small signal analysis. Let me remind you that the CE amplifier circuit that we had talked about earlier essentially is this one. This is of course a circuit which we have met before, but we have discussed only peripherally. What we had discussed earlier is a DC biasing circuit or DC biasing of this particular circuit, which is of course potential divider bias with emitter feedback. Now, in addition to all of these things, what you have are three capacitors, CB1, CB2, which are called blocking capacitors, and an emitter bypass capacitor CE. CB1 is used to connect a source Vs to the circuit. The Rs that you see here is just the source resistance. So every source of course comes with some resistance. Ideally the source resistance should be negligibly small, but we don't really live in an ideal world, so the source resistance can sometimes be substantial. On the other side, CB2 connects the circuit to RL, the load resistance. This could of course be a speaker or maybe the next amplifier stage in a multi-stage amplifier. Basically whatever is drawing the current and voltage from your amplifier. Now, why is there this CE in the amplifier circuit? Well, we will explain this soon, but let me just point out that as far as DC analysis is concerned, there is no signal and you're worried only about what happens if you turn on the battery VCC. These three capacitors CB1, CB2 and CE will basically behave like open circuits, which means they will detach the source and the load from the circuit, and also CE being an open circuit will just leave RE as a single thing that you have, and this is the circuit that we had, and this essentially will be your DC bias circuit. This is the circuit which we analyzed in some detail in the last video. We also saw that this particular circuit has rather nice bias stability. Current IC does not change very much even though parameters of the transistor change. And one way to understand that is basically this. Notice that RE stabilizes the circuit against bias variations. In other words, if various circuit parameters change, like the transistor beta or the temperature, so that the transistor ICO, all these might cause a change in the bias current. But if, for example, if IC rises, so will IE, and that will make the drop across RE go up. So this will move the emitter voltage higher and decrease the base emitter voltage. But remember, even a tiny decrease in the base emitter voltage will actually drastically change the IE and consequently the IC, and it will try to bring the IC down. What this means is that RE provides some sort of negative feedback to the circuit. Anytime IC tries to go up, RE's or the effect of RE essentially pulls IC back down. Not necessarily to the value it was before it tried to go up, but what it will do is it will not let the IC rise as much as it would have risen. This of course is a secret behind RE acting as a bias stabilizer. However, you should also realize that the same thing is really bad when we are thinking in terms of amplification. After all, even during amplification, the current IC will change. Of course, it will change because of a different reason, because there is a signal which is causing the currents and voltages in the input side of the circuit to change, and that will cause the output to change. But RE, of course, does not know between a good variation and a bad variation, RD would try to act as a negative feedback even there. And this will mean that the amplification which the circuit is supposed to provide, the output voltage should change a lot more than the input voltage signal changes, is going to be hampered by the presence of RD. RD will effectively bring the gain down. Now that is exactly why the capacitor CE is in the circuit. Since your signal is of some reasonably high frequency, what will happen is that the capacitor essentially will behave like a short circuit as far as the signal is concerned. Note that it behaves like an open circuit as far as the DC is concerned. So it does not show up in the DC bias circuit. But as far as the signal is concerned, it will behave like a short circuit. So what will that do? It will actually short the resistance RE out of the circuit. So this way you have the best of both worlds. RE provides bias stabilization, but at the same time, RE is shorted out as far as signal is concerned, and that's why you do not have a drop in the gain because of the RE. In the last video, we studied about DC biasing. In particular, we studied how to calculate the bias voltages and currents which will be caused because of the VCC battery. That is, we have studied this circuit in some detail already in the last video. Now we want to talk about the effect of the signal on top of it. And the method that we will use essentially involves the principle of superposition. But now you should object to this. Why? Because the circuit here is non-linear, right? It involves a transistor whose behavior, whose voltage versus current characteristics is not linear at all. And superposition principle, strictly speaking, cannot be used for non-linear circuits for the simple reason that superposition ultimately says that if you put in two different inputs, the output is the sum of what you would get for those two inputs separately. And that, of course, is something which is true only for linear circuit components. Now, the reason why we can still use superposition despite the non-linearity is because we are dealing with small AC signals essentially using Taylor series and keeping only the first order terms. Now this should actually sound pretty familiar to most of you, basically because what we are describing here is nothing but the same method that gave us, say, the two-port network theorems. We were essentially dealing with linearized versions of variations. So let me warn you that whatever analysis we do here is valid as long as the signal that is used is small. If the signal is large, then this analysis will actually not make much sense. But small signals are basically what you would usually start with. After all, your amplifier is meant to amplify, produce a large version of the input, and if the input is small, then the output will be of a reasonable size. If the output tries to be too big, it will drive the transistor into saturation or cutoff, and that way you will lose, well, fidelity. You will not get an output which looks sort of like a magnified version of the input, but will be distorted. So now, if we want to use superposition here, the procedure would be somewhat like this. we have already done one part of the superposition story. You treat Vs as absent, that is, replace it by a short, and figure out what happens due to VCC. Of course, there we did not even care about whether Vs was there or not, because as far as DC analysis is concerned, the capacitor CB1, the blocking capacitor, essentially blocked the source out from the circuit. Similarly, the blocking capacitor CB2 blocked RL from the circuit, which is why your DC bias circuit does not have any trace of the source or the load. Now, what happens when we look at it the other way around? That is, we want to now talk about the effect of Vs, or the effect caused by Vs, under a situation where VCC is 0. What does that mean? Of course, if VCC is 0, then this point up here is really the same point as the ground. It's actually joined to the ground, right? Remember, battery VCC here simply means that there is a battery of size VCC connected between the ground and this point up here. So if VCC is 0, this point is really joined to the ground by a wire. So note, the resistance R1 here has been connected between this point and the ground. So what you have is effectively a parallel combination R1, R2. RC, of course, is connected to the collector on one end and to the ground on the other. That is why it's connected here. RL, of course, is on the other side of CB2. And we have CE, CB1, etc. as before. And this is a small signal AC circuit. Now, if the frequency range of the input signal is sufficiently high, as I said before, all the capacitors that you can see will behave like short circuits. So you can replace them by just stretches of wire. If you do that, what you end up with is this, the effective circuit for what are called mid-band frequencies. In the effective circuit, the RL and RC, which were separated by the CB2, the second blocking capacitor before, are no longer separated. They are both joined together on both ends, so they are in parallel. So you have the RL-RC parallel combination here. We also have the R1, R2 parallel combination on this side. Remember the RE, this resistance has gone away because CE, which was parallel to it, is shorted at high enough frequencies. And we have the signal on this side. So this is the effective circuit for mid-band frequencies. Note carefully that I said mid-band frequencies and not high frequencies. Now that might seem strange because, after all, once the frequency is high enough that you can treat the three capacitors on display as shorts, for any higher frequencies you would be able to treat them as shorts even better because the impedance is going to go down further. So why is this effective circuit for mid-band frequencies only? Well, the answer really is that the transistor itself begins to behave differently at high enough frequencies. And why does it happen? Well, the real details may be pretty complicated, but there's one easy thing that you can always think about. After all, transistors have junctions, right? The collector-base junction and the base-emitter junction. Now, in any PN junction, you have a depletion region which is devoid of charge carriers, and you have conducting regions, either P-type or N-type, on either side. So basically what you have is effectively an insulator sandwiched between two conductors. This, of course, gives rise to capacitances. These are not capacitances you want, these are stray capacitances which come in because of the way transistors are constructed. And what will that do? These capacitances are actually pretty tiny, which is why you can actually ignore them. Notice that these capacitors, for example, the capacitor which you have in the base emitter junction would effectively sort of be connected between the base and the emitter across the base emitter junction. So what would it do? If it carried current, it would actually divert current away from the actual transistor. It will just sort of reduce the effect of the transistor itself. Now, this stray capacitance, which is there between this junction, of course, this is not the only junction. You have a capacitance between the collector base junction as well. And although there is no collector emitter junction, you also have a stray capacitance between the collector and the emitter. These are all effective capacitances really, but it's also easy to understand why you have a capacitance between the collector and the emitter. Remember, collector and emitter are much better doped than the base, which is thin and very lightly doped. So the base also behaves sort of like an insulator between two conductors. So it's easy to understand why you have these effective capacitors, the base emitter, the base collector, the collector emitter capacitors, which are all things which will divert current away, which will provide alternative current pathways for current to flow away from, well, the active path. Also, as far as the output is concerned, any current which goes through this path does not go out into the load. So all these will negatively impact the working of the transistor, or the working of the transistor as an amplifier. Now, even at reasonably high frequencies, the impedance of these capacitors is actually very, very high, for the simple reason that these capacitors are really tiny, as opposed to, say, microfarad order capacitors, or hundreds of microfarads or millifarads order even capacitors which you will connect as CB1, CB2 and CE. These capacitors are of the order of nanofarads or so, much, much smaller, even picofarads, 10 to the minus 12 farads, that is. So at frequency ranges where the actual capacitors which you connect in the circuit behave like shorts, at the same frequency range, it's possible for these capacitors, the stray capacitors, to have huge impedances and effectively behave like open circuits. Only when you go to very high frequencies does this happen, does the impedance of these pathways become low enough so that they begin impacting the performance of the transistor amplifier. So at very low frequencies, the blocking capacitors essentially will block the signal from going in. That's what CB1 will do. CB2 will block the output signal from going out to the load. In the CE, will not have a small enough impedance, so there will be negative feedback on the emitter pathway, which will reduce the gain. All that will happen in low frequencies. In very high frequencies, on the other hand, these capacitors, the ones which you have connected, will behave like shorts, but these stray capacitors will provide alternative pathways for current to flow, again impacting the performance of your amplifier. Somewhere in the middle of this, there's usually a large range of frequencies for which the impedance of CB1, CB2 and CE is very small, whereas the impedance of these CBE, CBC and CCE, the stray capacitors, is still rather huge. So for the mid-band frequencies, you can actually ignore all these extra capacitors that you have drawn. So in the mid-band, there are no capacitors in the circuit, neither actual capacitors which you connect because they have been shorted out, nor these stray capacitors because they are still open circuit. So you have effectively a range of frequencies over which the amplifying action of the transistor is frequency independent, or at least almost frequency independent. So if you look at the gain of the amplifier against the frequency, you will find that at very low frequencies the gain is rather small. As I said, the source cannot even deliver its signal onto the transistor because it's blocked by CB1 and so on. And then as you raise the frequencies, what happens is the gain rises, then it plateaus out, stays flat. So it sort of looks like this. If you were to plot a graph of the gain versus frequency, it would look somewhat like this. So at very low frequencies, it's nearly very small gain, rising till it sort of flattens out here. And then at very high frequencies, the effect of these extra capacitors kick in, and that causes the gain to drop again. in between, in this range of frequencies, the gain is nearly flat, and this is what is called mid-band. Why is there a mid-band frequency at all? That's because of the huge size mismatch between CB1, CB2, CE, which are huge capacitances compared to the stray ones, CBE, CBC and CCE. That is why there is a big frequency range in the middle where you can treat these as shorts and these as open. And that is your mid-band frequency range. In the rest of the video, we are going to analyze the effective circuit for mid-band frequencies. And the weapon that we are going to use is basically this. We are going to replace the transistor, which is a complicated device, by an effective circuit. So the effective circuit we are going to talk about today is basically what any two-port network has. Remember, the transistor has only 3 legs, but we can treat it as a two-port network simply because the emitter is actually common here between the input and the output. And as we have learned in an earlier video, which you should definitely review now if you have forgotten all about it, we can replace two-port networks, especially when we are talking about variations or small variations about a quiescent point value, by various equivalent circuits. We could use the Z parameter, the Y parameter, or the H parameter equivalent circuit. If you do not remember the H parameter equivalent circuit, I would definitely advise you to go back and take a look at the video in which we discuss that. We are going to use the H parameter or the hybrid parameters equivalent circuit to describe a transistor. Why? Well, I will explain that later. Why the H parameter and not the Z or the Y? Well, just to remind you, this is what the effective circuit would look like. On the left here, you have this black box inside which you have your transistor, where the emitter is connected between both the input and the output. And because the base is here, this is the emitter line, so the input voltage here is small VBE. Just to remind you, the small letters here denote fluctuation. So the actual voltage VBE here would be, actual voltage VBE, the base emitter voltage, is actually a sum of two pieces. The DC or quiescent point value, which is really denoted by what I've written down right now, or VBEQ, plus a variation which is the so-called AC value, and that's written using small letters. Similarly, small IB, small IC, these are actually variations. So actual IC is a quiescent point IC, or the DC IC, that what we calculated, the thing we calculated in the last video, plus the fluctuation small IC. Note that these fluctuations are basically your input signal and output signal and so on. So when you say gain, voltage gain, you don't really mean the output voltage divided by the input voltage. You mean the change in the output voltage divided by the change in the input voltage. So there's these small letter quantities which are really under consideration. Now this is of course what your original actual circuit is, or at least circuit component, the transistor is. The effective circuit for that in the hybrid parameter version uses a resistance in series with a voltage source. HI is the input impedance, HR is a reverse transfer voltage, HREVCE is the source, HF is a forward transfer current gain, and HO is the output impedance. So once again, please review the hybrid parameter discussion that we had earlier. The only special thing about this is I put in an extra letter E in each one of these things, in each one of the H parameters. This is to show that we are talking of the common emitter H parameters. The circuit configuration where the emitter is connected between both the input and the output of your two-port network. Just to point out, you could have used common base or common collector H parameters to analyze the circuit just as well, not just as easily, but just as correctly. If you had used the common base circuit, you would connect it differently. You would connect the base between these points. After all, the transistor is the same no matter whether it's in the CE, CB or CC mode. It's just that, the common emitter amplifier is easiest to analyze using the common emitter H parameter. As you will soon see, the analysis is reasonably complicated. So, why make life any more difficult for ourselves? We will use the one which is best suited for it. By the way, these parameters HIE, HRE, HFE, HOE, they depend on the quiescent point value. They remember are partial derivatives which you calculate for nonlinear functions. So they definitely depend on where you are evaluating these derivatives. But over a large range near the middle of the characteristic curves, these are nearly constants. So we will treat them as more or less constants. Of course, you will find plenty of references both on the net or in textbooks about how these parameters vary with voltage, temperature, frequency and so on. But for our purpose, we are going to treat them as constants or approximate constants. So the job essentially is to actually change the transistor here. And what I have done is I have actually split the RC and RL into two pieces. RB, of course, here is nothing but the R1 parallel R2 that you had. The reason why I am doing that is to sort of signify a rather important point, which is this. This piece is, of course, only the transistor. But which one is the amplifier? The amplifier, of course, is, and this is an important distinction which will become useful to keep in mind, is really this part. This part, the source, is of course outside the amplifier, is looking into the amplifier, feeding signal in, and RL is a load which is outside the amplifier, is taking the output. RC is actually inside the amplifier, which is why I have actually split up the RC parallel RL combination into two separate resistances. Remember, there was an CB2 here, the blocking capacitor, but that is treated as a short because we are in the mid-band region. So there are two distinct amplifying elements here. One is the transistor itself, which is doing the amplifying, but the transistor alone is not the amplifier. RB and RC are also connected to it. You will have to remember this when we analyze the transistor circuit, and you will always have to be careful as to which, when we say gain, for example, which gain are we talking about? The gain of the transistor alone or gain of the circuit? We will soon see that there is a distinction between these two things. Now, what we need to do, of course, is replace the transistor which is in this black box here with two terminals on this side and two terminals on this side, two distinct ports sticking out. Replace this by the H parameter equivalent. So basically this is the same circuit as this one, and since the illustration of RC and RL as being one being inside the amplifier and the other being outside has already been done, I have again simplified my life a bit by replacing them by a single parallel combination RL prime. So we have RS vs RB on this side as before. We have RL prime on this side, which is actually the RC RL parallel combination up here, and the blue region, which is the transistor, has been replaced by its H parameter equivalent circuit. Now we will go on and analyze this circuit. Just to point out one thing, what are we really trying to find out? We are trying to find out the current gain, the AI, which is of course the ratio between the output current, which is IC. Remember, IC current is the current which is going outside, actually, and divided by IB. Actually, it's minus IC by IB. for the simple reason that the output current is really this current. This is the output current, I0. The input current, II, well, which one is the input current? That depends on whether you are looking at the gain by the transistor, where IB is the input current, or gain by the circuit, where IN is the input current. Notice that because of the RB, which will take away some part of this input current, IB is not the same as IN. So this AI is the gain due to transistor alone, minus IC by IB. AV, the voltage gain, is of course VCE, the output voltage, which is actually the output voltage anyway. Even if you consider the RC-RL combination, the voltage is VCE across all of them. Of course, the output voltage is the voltage across RL, but it's also the same as the voltage across RL prime, so no difference there. Similarly, the input voltage, well, VBE is the input voltage to both the transistor and this part of the circuit. So that's AV, which is VCE by VBE. Again, remember, these are just variations and not actual values. However, we would also have to talk about the current gain with the load, which is how much of the output current actually goes into RL. IO, of course, is minus IC, but that doesn't go entirely into the output. Because of the RC-RL parallel combination, the output current branches into these two pieces. So even if you are talking about the output gain, current gain, you have to be careful. Are you talking about the current gain due to the transistor alone, which is AI, this one, or are you talking about the current which is being delivered to the load as opposed to the current which the transistor delivers? They are two different things. So this may become quite confusing because you may find different expressions for current gain or voltage gain in different books. But in most cases, the source of the discrepancy is that they are talking about different things. Which one of them is the actual current gain? Well, all of them are. Depending on what your viewpoint is, one is more important than the other. Sometimes both are equally important. Similarly, when you talk of AV, instead of talking about the output voltage VCE by the input voltage VBE to the transistor, you would want to talk about VCE by VS, where VS is the source voltage, right? So, and source voltage is not the same as the voltage VBE simply because this circuit will draw some current. Of course it will. IB is the current going in here. Some current will flow through this. So IN, some current is coming in. And that current is going to cause a drop across RS. So an important quantity to worry about is, if you look at this circuit from the point of view of the source, how much is the effective impedance of this circuit? That will decide how much current is going to be pulled in. This is called the input impedance. If the input impedance is high, then very little current is going to come in and the drop across RS is going to be small. Of course, it's really a comparative statement. When you say input impedance is high, you mean input impedance is high compared to RS. Similarly, on the output side, if the output impedance is low, then you don't really care about RC too much because most of the current which the transistor delivers will flow through RL in that case. So we will look at these issues of input impedance and output impedance in some detail in the next video. In this video, we will focus on calculating the gain of this circuit. And when I say gain, I mean this current gain and this voltage gain. Of course, we can easily translate one of these current and voltage gains into the other ones. So this is what our aim is. So we will now actually carry out the calculation for the current gain and the voltage gain. Just to remind you once again, these are current gains and voltage gains with respect to the transistor. But once you have those, you can easily change the expressions to the other current or voltage gains which you may want. So right now we need to calculate AI and AV, ratio between IC and IB specifically, and VCE and VBE. So just to start, take a look at this. IC is the current going into this node here. So this is IC, and what it does is it branches into two parts. One goes through this current source, which of course always carries a current of HFE IB. Is a current controlled current source. The current here controls the value of this current source, but it's fixed. Once IB is fixed, it's fixed at HFE IB. So what you have here is this. IC, the current, is going to have two pieces. One is HFE IB. The other is the current flowing through this. Now you have to be a bit careful here. HOE is an admittance and not a resistance. So current through it is actually the voltage across it, which is VCE, times the admittance. So it's HOE times VCE. Well, VCE, as you can already see from this, just by looking at it from the other side, is actually the same as IO times RL prime or minus IC times RL prime. Well, this immediately gives us a way of writing IC in terms of IB, which is, you just take this expression, stick it back here, and you get HFE IB minus HOE RL prime times IC. And now all you have to do is change IC over to the other side and divide by cancel out the common factor to end up with this result. IC is HFE IB by 1 plus HOE RL prime which implies that the current gain, the result that we wanted, let's write that on red. This is one of the results that we wanted. Minus IC by IB is simply minus HFE by 1 plus HOE RL prime. Well, that was not too difficult, right? Well, there's only one more part left, which is calculation of VCE by VB. We already have VCE. So if we can write VB in terms of IC or even in terms of IB, because we know the IC by IB ratio now, then we're through. So let's do one thing. Let's just get rid of this part from the slate so that I have some space to write the thing in. Well, I already know what IC by IB ratio is. In fact, even if I forget, I can read it off from this AI expression. AI, remember, is minus IC by IB. So all you have to do is just drop the minus sign and you get IC by IB. So this part is done. Let's now look at VBE. Well, VBE is actually straightforward. VBE is the voltage here, which is the voltage drop between this point and this point. So if you go from this point to the ground, along this path, you encounter two things. You encounter the resistance HIE, and there's a voltage drop HIE IB due to that. You also go through this voltage source HREVC, that's the other drop. So VBE is just the sum of these two. So your job, well, the simple thing would be to write everything in terms of one factor, let's say IB. So you want to take HIE, keep HIE in, move IB out of the bracket. Well, the VCE is minus ICRL prime. So this is minus HRE RL prime, right? And then you need to replace the IC in terms of IB. That's a further HFE by 1 plus HOE RL prime. So VCE by VBE, which is our voltage gain AV, what's that? That's simply minus RL prime by this quantity HIE minus HRE HFE RL prime by 1 plus HOE RL prime. That's the ratio between the RL prime here and this factor here, of course you still have the IC by IB ratio to put in. And IC by IB ratio is simply HFE I1 plus HOE RL prime. And now that we have put this in, you can simplify this expression by multiplying through by this, of course, and you end up with minus HFE RL prime. That's the numerator. The denominator simply becomes, if you multiply through by this, HIE plus HIE HOE minus HRE HFE into RL prime. These are the two expressions that you need: AI, the current gain, and the voltage gain AB. As we discussed before, you can use this and calculation of the input impedance and the output impedance to figure out the other current and voltage gains as necessary. We are going to discuss them in some detail in the next video. But before we sign off from this one, I need to point out one thing. I promised at the beginning, when we started using the H parameters, that I will explain to you why I am using the H parameters and not say the Z or the Y parameters here. The expression that you end up with does not really look that simple, so that hardly sort of justifies the use of H as opposed to Z or Y parameters. But what is important is to keep in mind the typical relative sizes of these objects. So in a common emitter amplifier configuration, HFE is rather large. In fact, as we will see, this is of the order of beta of the transistor, so that's 100 or 200 or more. HIE is typically of the order of kilo ohms. It's a resistance. Well, actually it's not 1 kilo ohm, but it's of the same, of a reasonably close order, and that means it's not a negligible resistance. You cannot drop it compared to the other things in the circuit. On the other hand, HRE is actually rather tiny. There's a physical reason for that. We will explore that soon. But for the time being, let's just focus on the values. For a typical transistor, HRE is of the order of 10 to the minus 5 or so. So even after multiplication by HFE, which is here, is still rather small. HFE is of the order of 10 to the 2. So 10 to the minus 5 times 10 to the 2 is still 10 to the minus 3, 1 in 1000. Also, HOE is really very small. Well, strictly speaking, HOE being very small doesn't really make much sense because it's a dimensional quantity, it's an admittance. What is important is HOE times RL prime, which is dimensionless. Assuming RL prime to be of the order of kilo ohms is again very small, 10 to the minus 6 or so. Okay, this of course varies from transistor to transistor. I'm just giving you the rough ballpark values. What that means is HOE RL prime is a tiny number which you can ignore compared to 1. HRE is a tiny factor. So what this actually does for you is that it ends up giving you an expression for AI, which is as simple as minus HFE, and AV, which is just minus HFE RL prime by HIE. So this is the simplification which occurs because you are using the common emitter H parameters to describe the transistor. If I had used the Z or the Y parameters, the various parameters would have been reasonably large. All of them would have been sort of the same order, so the simplification would not have occurred. In the final part of the video, I'm going to try to explain to you why HFE and HIE are substantial for a transistor, whereas HRE and HOE are so small. And for this, what we will do is we will fall back on a physical model of the transistor that we had already met earlier, which is the Ebers-Moll model. Just to remind you, the Ebers-Moll model, in this case drawn for an NPN transistor, essentially uses two back-to-back diodes to talk about the base collector and the collector emitter junctions. And the difference between just having a pair of back-to-back diodes is that once the current, either the electron or the hole current, enters into the base, is swept into the other side, and that's why you have this alpha R ICD pulled. Whatever ICD you have is pulled to this side, and whatever IED you have is pulled to this side, alpha F IED. So this is the Ebers-Moll model, which is a reasonably good approximate model based on the physics of the transistor. Now in the active mode, we saw that there is a further simplification, which is because this diode is reverse biased, the collector base junction is reverse biased. In the active mode, you can imagine that this is just an open circuit. You can drop it. Of course, when you drop it, ICD vanishes, so does this. So you're left with just this alpha F IE on this side. Notice that once you no longer have the ICD, IED and IE are just negatives of each other. So what used to be alpha F IED pointing in this direction is now the same as alpha F IE pointing in this direction. In fact, we can just drop the F suffix because there's only one alpha in this situation. Now this is what you use to describe a transistor approximately in the active mode. We already talked about how to use this in the DC bias calculations, where what we did was essentially replace the diode by the cut-in voltage, which is the voltage drop across a forward bias diode. Now that is for the DC part of the calculation. Now what we want to do is talk about the AC part, or fluctuations. Now the thing is really rather simple. As far as DC fluctuations is concerned, what will the diode here look like? Just to remind you, the diode here really looks like an cut-in voltage, opposing cut-in voltage in series with a series resistance, a diode forward resistance, and an ideal diode. Of course, because it's forward bias, the ideal diode can be replaced by a short. And when we are talking of fluctuations, the cut-in voltage, which is a constant, does not fluctuate, so does not contribute. So all you are left with is a single resistance here. So basically the effective circuit that you have for AC becomes this. This is this actual circuit, but you can replace a diode by a single resistance, the emitter resistance in this case. This really is the diode resistance of the base emitter junction. And this is, of course, alpha IE. I've just dropped the F because there's only one alpha to talk about. Now, just as we had discussed before, for the effective DC circuit, or approximate Ebers-Moll DC version, you can actually modify this circuit so that it becomes easier to use it in the common emitter configuration. Having something in this lead, in the emitter lead, is really, well, not so convenient if you're dealing with the common emitter configuration. And so what you can always do is replace this circuit by putting a short between the common point and the emitter, replacing the current source here, alpha IE, by an equal current source, but expressed in terms of IB, beta IB, where beta is, of course, alpha by 1 minus alpha. This is the same calculation as the one we had done before. You have to remember that sign switches, so beta IB points this way. The only real difference is you have to replace the resistance which was here by resistance here. Remember, the only thing that this resistance really does is produces a voltage drop between emitter, which is this point, and the base, which is this point but also this point. So RD essentially produces a voltage drop between the emitter and the base. And whatever equivalent circuit you're talking about should produce the same voltage drop. The only thing you have to remember is IE and IB are two entirely different currents. And so now that you're putting the resistance here instead of here, to get the same drop, you will need to put a much bigger resistance. This is something which you should work out yourself. To get exactly the same drop, what you need to put in is RD times this extra factor beta plus 1. And this, well, this is not even an equivalent circuit. This is the same circuit as this one. All we have done is redrawn this in such a way that the emitter points downwards, base is to the left, and collector is to the top, which essentially makes it look very much like the way the transistor is connected in the common emitter configuration, at least in our circuit. So all we do is just take, if we wanted to analyze the transistor circuit just by using this. All we would do is take whatever transistor is here, just replace it by this connection. And you would of course agree that this is a much simpler effective model than the full hybrid parameter effective model. But as we explained, this is something which follows rather directly from the physical picture we have of a transistor. This is not exact, but this is pretty close to being accurate. Now, it's easy to calculate the HFE, HIE, HOE and HRE values for this circuit just by using the standard method that we had discussed earlier. That is, find out the input impedance, output impedance, etc. in the proper manner. And you should do it. This is a nice exercise to carry out. However, there's another way to see what the H parameters of this circuit will be, which is simply redraw this a bit. We just draw this circuit in this fashion. Okay, this is not a different circuit. Let me just show you the two things side by side. Let me just move this picture below so that it sits besides this. Now it should be obvious that all we have is we have pulled this single point E into this long wire just to make it look like E is connected to both the input and the output in a two-port network. And now base was connected to the emitter via this single resistance beta plus 1 RE, which is also exactly what is happening here. And the collector was connected to this point, which is the emitter, through this beta IB current source. So this is really not an equivalent circuit. This is exactly the same circuit once again. But now that you have drawn it like this, it is obvious what the H parameters of this circuit are. You can immediately read it off from the circuit. Remember, the H parameter equivalent network was HIE here, then HREVCE here. On this side you have HFE IB and you had HOE in parallel to that. So here it's easy to see that HIE is nothing but beta plus 1 RE. HFE is nothing but beta. And at least for this approximate model, HRE, which is the voltage source factor which is sitting here, for this equivalent circuit HRE is exactly 0. And HOE is admittance of this open circuit, which is of course also 0. There is no parallel branch here. So at least for this effective approximate circuit, HRE and HOE are exactly 0, which explains why they are very tiny in the real transistor. They are not exactly 0, but they are very small. Also, this should give us a reasonably good handle onto the values of HIE and HFE. HFE is beta, so that's of the order of 100, 200 depending on the transistor. What about HIE? Just to remind you, RE is a diode forward AC resistance which as we worked out was 26 millivolts roughly by the emitter current. This is the DC emitter current, DC bias emitter current. Typical DC bias currents of the order of few milliamperes. So RE is of the order of 10 ohms or so. That's a very tiny resistance. But notice that HIE is multiplied by a further factor of beta, which is of the order of 100. So HIE turns out to be of the order of a kilo ohm. So HIE and HFE are substantial. HRE and HOE are very, very tiny. In this approximate model is exactly 0. And so using the H parameters, while that might lead to a reasonably complicated looking expression, ultimately leads to an approximation which is rather nice. And that approximation is a pretty good approximation for most practical purposes. In fact, you should have also realized by now that we could have analyzed our circuit without using the full glory of the H parameters just by using this simple effective circuit, just one resistance beta plus 1 RE between the base and the emitter and a current source beta IB. That would work fine for most practical purposes. In fact, in our later videos, when we talk about analyzing various transistor circuits, we are actually going to use this effective model. Most of the time. Sometimes when we want to do things more accurately, we are going to fall back upon the full glory of the H parameters. But very often we are just going to use this effective approximate H parameter model, or what is often called the resistance current source model of the transistor. So that's for coming videos. Bye for now.